Well, hello again. So, this is the third part in the series on the wave-particle duality theme, and this will be the concluding episode for this time, and it's where I will try to outline a program that I think could perhaps resolve this wave-particle duality issue that we have been living with for a century by now. And as you might have already gathered from the images here, the electron spin is going to play a central part in this story. So we can show a little bit of timeline again. In 1922, we have the Stern-Gerlach experiment, which I will talk about in a moment. In 1925, the idea that the electron has some kind of intrinsic spin is suggested by a number of physicists. Then this idea seems to be hijacked by theoreticians, notably Pauli, who was in the beginning against the concept, but then apparently changed his mind. And then Dirac gets his hand on this concept too, and then derives spin from his equation and declares it a relativistic phenomenon, of course. Um, well, so here we see the Stern-Gerlach experiment set up. So what we have is silver atoms being put here through a inhomogeneous magnetic field. And then the outcome seems to be that they end up in discrete positions. It seems like the atoms are either in some kind of up state or down state, and nothing in between those. So the initial purpose of this experiment was to detect what was then called space quantization in Bohr's model of the hydrogen atom. And as I interpret it, it's like more or less finding out whether these quantized angular momenta orbits really exist or not. However, subsequently, the experiment was instead interpreted to demonstrate quantized spin. Now, the silver atom has, of course, many electrons and is a more complex structure than a single electron. So, interpreting the Stern-Gerlach experiment is perhaps not as straightforward as we might hope. But then the question is, could we do the same experiment for a single elementary particle like the electron? Well, there's a problem here, and that is that the electrons are not electrically neutral. The electron is a charged particle, and if we put it through a magnetic field, it would experience a Lorentz force. So it would, presumably go through some kind of circular trajectory, and then, it would mess up the experiment, to say the least. Probably. But have been modified experiments done where they instead, as far as I've seen, show the electron switching between spin states, and the difference in magnitude of these is Planck's constant, h bar. Now, inevitably, I guess I would have to comment on this notion that electrons have either spin plus minus 1/2 h bar. It's stated everywhere if you start to read about anything about electron spin, and it should be emphasized that this is a purely theoretical consideration based on the Dirac equation. if you do measure the spin, the magnitude of the spin according to classical wisdom, then it turns out to be h bar and not 1/2 h bar. And just to show you that I'm not making this up, this is from the Wikipedia article on spin, where you have the so-called G factor introduced. And where does that come from? Well, the value 2 of the G factor, which then happens to be 2, of course, it comes from the Dirac equation. So if you measure something which is h bar and then we have some factor here, well, then it's more or less dictated that, okay, so then since Dirac equation is true for some reason, then the electron must have spin 1/2. Now we go back a little bit to what we talked about in the previous episode. So here we have the electron double slit experiment. And my idea here is that, well, could it be that what we're actually observing here is the electron spin, which is sort of deflecting the trajectory of the electron somehow in a way somewhat analogous to the Stern-Gerlach experiment. If we recall, the only thing used here was an inhomogeneous magnetic field. So you then might then ask, well, where does that magnetic field come from? Well, an electron is a charged particle, and each charged particle moving in space, it's according to the Faraday law, actually produces a magnetic field. And if we imagine the electron coming here and we open some other slit, maybe that is sufficient to create some kind of asymmetry in the magnetic field. And that gives it a momentous little impulse in some direction. This is, of course, speculation on my part, but it's an idea to consider maybe. Because is the conclusion then based on the experiments that the electrons can indeed have higher order spins, that the electron spin is in fact an integer multiple of h bar and not just simply plus minus 1/2 h bar, as we're being constantly told. Because if you recall, I mean, experiments, they do show that the quantum is h bar, and if this shows several, spots here, then, well, maybe we arrived at this conclusion. And then how can this move us forward? Well, if we now consider the results so far, okay, let's assume that the electron spin can indeed be an integer multiple of h bar. Well, what is the assumption in the Bohr model of a hydrogen atom? It's that the orbital angular momentum of the electron is quantized in integer multiples of h bar. And then we have the old formula for the energy of light quanta, which is the angular frequency times h bar. And, well, is this a coincidence? Is it like this mysterious entity here enters here in these formulas just by chance? That these are not related in some sense? Well, I would find that rather improbable. So, how do we put this puzzle together? Well, an early problem when people were trying to model the atom as an electron orbiting a proton or something like that, was that, well, if you have a charged particle which is accelerating, and if you move in a circular orbit, you are accelerating, then there's this Larmor formula from classical electrodynamics, which says that, well, this particle would radiate energy and thereby lose energy and consequently just crash into the center, and then the atom has, well, lost its shape. Now, well, what if we come up with the idea that, well, okay, according to the Bohr model, the orbital angular momentum L should be an h bar. But what if the spin of this electron is then the negative value of that? Well, then they sum up to zero. So maybe that could be some kind of heuristic argument at this point for how this spin could actually resolve an early problem, which was then just neglected. It was just forgotten, let's not care about the Larmor formula on that. But it turns out, I think, that the spin could actually address that early problem that we have. Now we come to the photon. And here I'm going to apply something which is a kind of powerful tool in the physics toolbox. It's dimensional analysis, which you can use if you don't have an exact description of exactly what's going on. But first we note that angular momentum, the dimension of that is energy times time. Now, in an electromagnetic field, there exists a natural time scale, and that is the period of one oscillation. So that's a natural time scale which we extract from this. And if we add to that, well, the angular momentum, according to experiment, is quantized. Well, if we assume that, during one oscillation, the atomic state can only accept quantized angular momentum. That is the entity that we should absorb. It's not a priori a certain amount of energy that we want to absorb, but rather quantized angular momentum. Well, if we just plug in this to the formula here, well, then we arrive at this relation. Now, so, well, this is the program that makes most sense to me. And somebody might argue that, well, wasn't this already tested back in the day? Didn't they try to build a Bohr model of the helium atom and so on? And didn't it fail? And so on. Well, there's one thing I would like to add to that, and that is that in the early modeling, there couldn't have been any spin-spin interaction considered. So that is a new component. And what that brings about, I cannot say, of course. There are many details missing here. It's just a skeleton of something, but to me, this seems like an interesting line of thought, and I hope this has inspired you to do a little bit of your own research and maybe build upon these ideas. So with that, I will say bye-bye for now.